Welcome to The Explainer. Today, we're going to decode a secret conversation that's happening right now, inside basically every electronic device you own. It's the hidden language of computer chips, and once you get it, you'll see modern electronics in a whole new light.
So, let's just dive right in. Take a look at any modern circuit board. It's like this super crowded city, just packed with microcontrollers, sensors, memory chips, you name it. And they all need to talk to each other. But, can you imagine connecting every single chip to every other chip? It would be an absolute nightmare of wires. So, how do they do it?
Well, the answer is actually pretty elegant. They use shared communication systems, which are basically the roads and traffic rules for this little electronic city. And two of the most popular, most fundamental protocols you'll ever come across are I2C and SPI. Now, they both solve the exact same problem, but they do it in completely different and pretty fascinating ways.
Let's start with the most obvious difference, the one you can literally see with your own eyes, the number of wires each one needs to get the job done. Honestly, this one little detail tells you almost everything you need to know about how they think. So first up, we've got I2C, which stands for Inter-Integrated Circuit. Its big claim to fame is its incredible simplicity. It uses just two lines for everything. That's it. Two little wires to connect a whole network of different devices.
And in the other corner, you've got SPI, or Serial Peripheral Interface. This one starts with a baseline of 4 wires just for one device, and then you have to add another wire for every single extra device you want to connect.
Okay, so this slide really lays it all out. On the left, you see I2C's 2 wires, SDA for the data and SCL for the clock. Super simple. But then look at the right. SPI has separate lines for data going out, that's MOSI, and data coming in, that's MISO. It's also got a clock, of course. And then there's that crucial 4th line, the slave select. That's the key to its whole system. So you've got to be wondering, right? With only 2 wires, how on earth does I2C manage a conversation with like 10 different devices? And why in the world does SPI need so many? Well, it all comes down to the language and logic that's baked right into the protocols themselves. The way I2C works is actually kind of brilliant. Think of it like a postal service. Every single device on that 2-wire bus has its own unique address, like a house number. When the main controller wants to talk, it just broadcasts that address onto the shared line for everyone to hear. It's like sending out a letter. And this addressing system, that's the magic trick behind I2C's 2-wire design. Instead of needing a physical wire to pick a device, it just uses this software address. Yeah, all the devices on the line hear the address, but only the one that recognizes it as its own actually pays attention. The rest, just ignore it. And this brings us to the protocol itself. And you can see there's a lot of back and forth. It's like this polite little dance. The controller sends a start signal and the address, then it has to pause and wait for the target device to say, yep, got it. Then it sends a chunk of data and waits for another, got it. All this extra chatter creates what we call overhead, but it does make sure the message gets through reliably. Now, SPI, it takes a totally different, much more direct approach. Think of it less like a postal service and more like a conference call where the master chip is the moderator. It doesn't shout an address for everyone to hear. Nope. It uses a dedicated private line, that slave select line, to tell one specific chip, okay, it's your turn to talk. And all the other chips, they just stay completely silent because their line isn't active. And that dedicated wire is the entire reason SPI needs more pins. Each and every slave device needs its own private slave select line running all the way back to the master. It's a hardware solution to the problem, whereas I2C uses that software address approach. And you can just see the difference in philosophy here. An SPI transaction is brutally efficient. Master pulls the line low to pick a device, then boom, it's just a raw stream of data flowing in both directions at the exact same time. That's what full duplex means. And when it's done, the master just pulls the line high, game over. No addresses, no acknowledgements, just pure, fast data transfer. Okay, so we've got 2 clear contenders. We have the pin-efficient I2C with its addressing overhead versus the lightning-fast multi-wire SPI with its direct hardware selection. So let's put them head-to-head and figure out which one is the right tool for your job. This table really just boils everything down to the essential trade-offs, doesn't it? With I2C, you save a ton of pins, which is awesome, but you pay for it with slower speeds and more protocol complexity. With SPI, you get that incredible speed, and you can talk and listen at the same time, but it's going to cost you more pins and make your circuit board layout a bit trickier. So when are you going to reach for I2C? Well, it is the undisputed champion of pin efficiency.
If your main chip is running low on available pins, or you're connecting a whole bunch of simple devices like temperature sensors or real-time clocks where blazing speed just isn't necessary, I2C is absolutely your best friend.
But what if you need performance? If speed is the name of the game, SPI is the king. For things that need to move a lot of data and move it fast, like writing to an SD card, streaming data from a high-speed sensor, or quickly refreshing a color display, that minimal overhead and raw speed is exactly what you need.
And there you have it. You can now actually look at a project's requirements and make a really informed decision. You get the fundamental trade-off: the wiring simplicity and pin saving of I2C versus the raw, unadulterated communication speed of SPI.
So the final question really is for you. For whatever you're building next, what matters more? Saving every last precious pin on your microcontroller or pumping every last bit of data through per second? The choice is yours, and now you have the tools to make it wisely.